relation. Let's call this as, I denote it by tilde. What is it that it will do? It will take two elements from S, okay, and it will say whether it's related or not, right? So essentially, let me not make it very formal, and an equivalence relation, this, okay, right? Is that fine? So in the earlier case, I wrote it as a double arrow, okay. So what are the properties of this equivalence relation? You take any two sets, right? So you can either say A is related to B or not, right? So okay, let me put that in the context of itself, right? What are the properties? So A is related to A for every A in S, right? A is related to B implies B is related to A for every AB in S. And the third one would be A is related to B and B is related to C implies A is related to C for every A, B, C in S, right? These are the properties. Do you agree? Fine. So now we
Yes,
have
sir.
to prove that this divides into the entire class into equivalence classes, right? So how do you write that? How do you collect these things? Okay, the way you do it, you can do it mechanically, right? So fix some A in S. Okay, I'll take some arbitrary A. Okay, so I'll consider an equivalent class, let me call it as EA, okay, which is defined as all those B in S, that is the states in S, such that A is related to B, right? So in other words, if A can talk to B and B can talk to A, then I'll put that B into this set. Obviously, A can talk to A, so therefore A clearly belongs to EA, right? This is very clear. Fine? Is that okay? Ayush?
Yes, sir.
Clear, right?
Yes, sir. Yes, sir.
So you
Yes,
take,
sir.
so now the idea is this ES partitions, yes, okay. That is, what do you mean by that? If you take, for example, EA and EB, okay, so you take two sets. Either EA will be equal to this, or if you take intersection of these two, it will be null. Okay, this is what you should prove, right? Do you agree? Now, can you try to prove whether this either of them should happen, right? If you take A and B, right? So, for example, suppose let's look at two cases now. Suppose A communicates with B, that is B belongs to EA, right? Then we need to prove that EA is same as EB, right? Do you agree? Then I won't even prove, you can see this clearly, EA equal to EB. Why is that the case? Can somebody tell me? What is EB? All those states which can be communicated from B, right? What is EA? All those states which can be communicated from A, right? Suppose B belongs to A, what does that mean? So B can communicate with A, but all those states which B can communicate, A can also communicate, right? Therefore, EA should be equal to EB. Do you agree? Is that
Sir,
fine? Yes.
sir, if there is a state C and
Hmm.
that also communicates with A, but
Huh?
here we are partitioning it into EA, like EA is partitioning S. So then C will not be able to communicate with A then.
No, if, for example, C belongs to EA, right?
Okay.
Then C can communicate with A. It can go back and forth from A to C and C to A, right? That means C can also communicate with all those states that A can communicate. That is, all those states in EA, it can communicate. Therefore, by definition, so if you construct a set EC, EC will be equal to EA, right? So think of it as individuals as states, and if they hold hand together, then they are equivalence class. Okay. So the claim is equivalence class partitions the entire group into two parties, right? Not two parties, multiple disjoint parties. What is the worst case scenario? One party, right? Everybody holds hand with each other, right? I mean, in other words, if there are four people, A, B, C, D, then A can talk to B and B can talk to C, C can talk to D, and vice versa, right? That forms a chain. It is one group. If you want to have two groups, what do you mean by that? Essentially, there is a breakage of link, right? So let me give you an example, then it will be clear, I think. So I take states 0, 1, 2, 3, 4. Okay. So let's look at these things. Sorry. Okay. You can put appropriate probabilities. Okay. In all of this, such that the probabilities are non-zero. Okay. What can you say about this? 0 can talk to 1. 1 can talk to 2. By the property of equivalence, 0 can talk to 2. We proved this, right? Do you agree? Therefore, 0, 1, 2 belongs to the same class. Do you agree? That means E0, it is all those states that 0 can talk to. 0 can talk to 1 and 1 can talk to 0. Therefore, 0 and 1 are in the set 0, E0. So, E0 is same as E1 is same as E2. Do you agree? Okay. Let me call this as E1. Okay. What about E3?
Sir, sir, here 0 cannot talk with like 2 directly. So E0, how it is
No.
E0 equal
So
to E2?
you remember the definition. So what do you mean by 0 talking to 2? That means P0 to 2 in some step n is greater than 0. For example, I'll just give everything as half, okay? Half everywhere. Okay. What is the probability that it can go from 0 to 1 to 2? This is at least 1 by 4, right? At least 1 by 4. Right? So which is greater than 0, right? In what? How many steps? 2 steps. So P02 in 2 steps is greater than 0. Therefore, 0 can communicate with 2. And similarly, 2 can communicate with 0. Why? I can start at 2 and go to 0 in 2 steps with the probability of at least 1 by 4, which is greater than 0. Therefore, 0 can talk to 2 and 2 can talk to 0. Therefore, they communicate with each other. Do you agree?
Yes, sir.
Okay. So it's not about communicating in one step. It's communicating in n step, any n. That's very clear. Ayush?
Yes, sir.
Huh?
Yes, sir. Yes, sir.
Okay, fine. So now let's look at E3. So 3, 1 can communicate with 3, right? For example, this could be 1, for example. Okay. So not 1, maybe it can go out, or I don't know. Did I make a okay? So 1 by 4, and let me make it as 1 by 4. Okay. So 1 can starting at 1, you can go either go to 2 or either go to 0 or can go to 3, right? But from 3 you cannot come back to 1. Do you agree? If you are in 3, you are gone.
Yes,
I
sir.
mean, there's no way by which this would be 1, right? You go back and forth, let's say. So that means E3 is nothing but 3 and 4, right? 3 can talk to 4 and 4 can talk to 3. Therefore, it's same as E4. Okay. But clearly, if you look at E1, so let me call this as E2. E1 intersection E2 is null. Do you agree? Because E1 is 0, 1, 2. E2 is 3 and 4. They are disjoint. It has broken this entire set into two parts. This is one set of states or communicating class. This is another. Right?
Yes, sir.
Is this fine? So you can, the argument is very clear, right? So EA equal to EB, or this is true. So for example, if A belongs to or B belongs to EA, then that means B can communicate with A, and therefore it can communicate with all the other nodes that A can communicate with. Therefore, B belongs to all the states in EB also belongs to EA, and vice versa. Therefore, EA equal to EB, right? On the other hand, if B does not belong to EA, right? The other part would be if EB does not belong to EA, that means what? It cannot communicate back and forth from any states in EA. That means if B can communicate with any other state, those states cannot communicate with the states in EA. Therefore, all those states don't belong to EA. Therefore, EA is not equal to EB, and they are disjoint. Right? Even if you say that one element belongs to EA, then all the elements of EB belongs to EA. Therefore, EB equal to EA. Right? Is this clear? I mean, you have to write it a little more formally, but this is the argument. Argument is clear. That's very important. Ayush?
Yes, sir.
Okay.
Clear, sir. Clear.
Yeah. So this is what you mean by splitting or equivalence. So the communication, this symbol forms an equivalence class, and therefore it partitions. Okay. Okay. Now let's start with a few other definitions. There is one more definition. This results in something. So there is this notion of recurrence and transient. Okay, we will see what those things are. Okay. Okay. So what do you mean by a recurrent state? So for a given Markov chain, a state. Let's consider some state I is said to be recurrent. Recurrent, as the name indicates, it will occur again and again and again. That means it will come back to state I again and again and again. Okay, and is recurrent if so what do you mean by recurrent? If I can communicate with J, implies J can communicate with I. Okay. Is that fine? That means if I can talk to J, then J should be able to talk to I. Then only we say that I is recurrent, and that should happen for every state, right? For example, 0, is it recurrent or not? See, 0 can
Yes,
talk
sir.
to 1 and 1 can talk to 0. Therefore, 0 is recurrent. What about 1? What can you say about state 1?
No, sir.
No, right? It can talk to 3, but 3 cannot talk to 1. Therefore, it's not recurrent. So 3 is also not recurrent, but 4 is recurrent. So 1 and 3 are transient states, while 0, 2, and 4 are recurrent state in this case. Okay. So I is said to be recurrent if I communicates with J, implies this. This is true for all J in states as. Yes. Okay. Set of states, yes. So otherwise we say that I is transient. Because why is this transient? So for example, if you are at 1, there is a chance that you will never come back to 1, right? So you'll go to 3 and you are stuck there, right? But whereas if, for example, well, is 3 recurrent? Sorry, is 3 recurrent or transient? We made a mistake. Okay, that's the hint. So is 3
Transient
recurrent?
only.
It's transient, right? Because 3 cannot communicate with 1. It says if I communicates with J, then J should communicate to I. But 3 does not communicate to 1. Therefore, I don't need 1 to communicate with 3. No, right? So 3 is not, so I'll mark in red those that are transient. Okay. This one is transient because the moment you hit 1, there is a chance that you will never come back. All right. So that's a transient state. Whereas 3 and 4 are recurrent. Okay. Because the moment you hit 3, you will come back again and again, infinitely often, right? Okay. Is that fine? Everyone?
Hello, sir. So I
Yes.
can talk to J and J can talk to I. This is the notion of equivalence also, right? Not implied and. I mean, is there an and between them?
Correct. So that and means communicating. But what it says is, if I can talk to J, then J should be able to talk to I. Then only we say that I is recurrent. Okay.
Okay.
Yeah.
Okay.
Okay. Any questions? Okay. So you know what a class is, right?
Sir,
Yes, sir.
Yes.
so this definition of recurrent, this just implies the communicate like we have defined above, no sir?
So it should belong to a communicating class, but there is another requirement, right? For example, see, I communicates with J. That always that should imply J should communicate with I. If you look at the previous example,
Mhm.
see one. What can you say about one? Well, is this a class? I mean, that comes to this question. So, is this thing that I have marked, right? This whole thing, is it a class? 0, 1, 2. So, what is a class? Okay, so equivalence relation for the communication double arrow will partition. So, what will it partition? See, 0, from
States.
0 you can go to 1, and 1 from 1 you can go to 0. So the 0 and 1 belong to the same set. 2 and
Yes
1
sir.
also belongs to the same set. So all these things belongs to the same set. But
Yes
3,
sir.
4 does not. I mean, it belongs to the same set. This is fine, right? So what is a communication? So this is called communicating classes. Okay. What is your question, Sumit?
No sir, actually I'm saying we have defined the communicate like both double arrow side, no sir? Like
Correct.
I double arrow
Ah.
J. Then sir, this is and this here we are defining that I connects to J implies J connects to I. This both implies that they are just communicating with each
Correct.
other only.
Exactly. See, for example, 1 communicates with 3, but 3 does not communicate with 1. So therefore, 1 is not
Yes, sir. One
recurrent,
is
right? 1 is not recurrent. Do you agree?
yes, sir. Yeah, because if it is recurrent, then it has to be 3 to 1 also.
Yeah, exactly.
Hello, sir.
Yes.
Sir, can you again define the definition of a class?
Okay, I'm going to do that. Okay, so this is called a communicating class, right? 0, 1, 2 is one, and 3 and 4 is another. Okay, so let's see what is a communicating class or a class. A class, C, is a subset of S. See, S is the set of all states. Okay, I'm taking the. In fact, class C is a non-empty subset. If you want to be very precise, you cannot take an empty subset. Non-empty subset of states, such that now, if you take I belonging to C, if you take this thing and you take any J, okay, not equal to I, okay, any state J not equal to I, then such that if I'll write it as if you take a state in C in the communication class and you take any other state not equal to I, then either J should be able to communicate with I and therefore J belongs to C, or J does not belong to C. Okay, fine. J satisfies what? J communicates with I, okay, and therefore J belongs to C. Okay, fine.
So that means, sir, a class will be a set of states which can have
Communicate with
equivalence
each other.
relation within each with each other.
They can communicate with each other. That's all, right?
Uh,
Then J satisfies this. So if J not equal to or, okay, or J does not belong to C. That means J, I communicate with J implies J, that is, I and J does not communicate with each other. Okay. Is that fine? Do you agree? Think of in terms of pictures. Okay. So if you have, if a state belong to that particular class, then it can communicate with all the other nodes in the class, and it cannot communicate with the neighboring, right? So for example, you look at 4. See, 4 can communicate with 3, but cannot communicate with 1 or 0 or 2 because there is no path there, right? I cannot go from 1 to 1 or 4 to 1 or 4 to 2 or 4 to 0, right? Forget about that. I cannot go from 3 to 1 also, right? Therefore, they belong to a separate class. Is that fine? Everyone? Rishabh?
Yes, sir. Yeah.
Okay. So now, what does this lead to? So let's we have two notions now. One is the notion of class, and the other one is the notion of recurrent. Okay. So what does that imply? So this results in a theorem. Okay. So or a result. So I'll state this and explain. Okay. For a finite Markov chains, either all states in a class are transient, or all are recurrent. Why is this? Can somebody tell me what is the proof and why is this true?
Sir, it is just by the definition that we have given the definition of the recurrent
Yeah.
only, sir. Because
So, for
recurrent is
example, if you have a class, right, that means the two nodes can communicate with each other. That's what it means, right? So, suppose one of them is transient. What does that mean? Or let's look at recurrent. If one of them is recurrent, what does that mean? What is the definition of recurrent?
It means if it is if
it can communicate with I, then it can
yeah.
communicate with.
Then I should also communicate with this also.
Right. So now, so suppose I can communicate with J, then J should be able to communicate with I. Right. Yes.
Sir, in the graph that you draw above,
Yeah.
Sir,
okay, go ahead.
In this, 0 and 2 are like recurrent.
No, not really, right? So that's something that we made a mistake, right? Now let's go by this definition. So you're right. That's what I was also about to say. See, what can you say about 3 and 4? It belongs to one class, right? That is very clear. Now, 3 and 4 are, is it recurrent by definition? See, if 3 can communicate with 4, implies 4 can communicate with 3. So they can go back and forth, right?
Yes, sir.
Right?
Yes,
is
sir.
that clear?
Yes, sir.
Okay. So now these two are definitely recurrent, right? Now I'm saying this is transient. Okay. What does that mean? Intuitively, that means you won't visit this state infinitely often. If you allow the Markov chain to run forever, you won't visit again and again and again. Okay. Why? There is some non-zero chance that at some point in time you will enter 3, and after you enter, it's a no point of no return, right? You just go to 3 and you go back and forth from 3 to 4, 3 and 4, right? So this is transient. So what can you say about this guy now?
Then if it moves to 1, then there may be a chance that 1 moves to another and doesn't come back.
To be recurrent, if I communicate with J, implies J for every J in S. That's correct. So I think we missed that. Can 0 communicate with 3? Yes, right? In 2 steps, with a probability of at least 1 by 8. Well, will 3 can communicate with 0? Not really. Therefore, this is also transient, right? So what can you say about 2? 2 can communicate with 3 with probability of at least 1 by 8, but 3 cannot communicate. So this will also be transient. So all the states within this communicating class is transient. Okay, so I take back my words, which I said, where I said 0 and 2 are recurrent. It's not really recurrent, right? All of them are transient, and 3 and 4 are recurrent. Is that fine now?
Yes,
Yes,
sir.
sir.
Yeah.
Ayush?
Yes, sir.
Okay. So now, suppose you have a state to be recurrent in. So let me draw a picture. So you have some set of states here, okay, and some set of states here, okay. Now, if one of them is recurrent, what does that mean? If this guy can communicate with anyone else, that guy should also be able to communicate, right? So now, suppose this guy can communicate with this, right? By definition, because it belongs to the same class, right? That means this also will be able to communicate with this guy, right? Do you agree? And this node can communicate with this node also, and likewise, because it's communicating class, right? So now, by this diagram, I can clearly see that this node can communicate with this node and vice versa, because there is this path which goes from here to here, and there is this path coming back, right? Do you agree? So that
Yes.
means all of them will turn out to be recurrent. Do you
Hello,
agree?
sir.
Yes.
Sir, can there be a transient relation be present in a class for a state? I mean,
What do you mean by that?
see, the left side there is a class. Okay, you have drawn just this a
So
class.
you're basically saying, if I have a Markov chain, can I break this into set of all transient and set of all recurrent? Is that what you're saying?
Sir, not exactly, sir. I am saying, sir, like the left class that you have drawn.
Okay.
Sir, can there be a state from where that is transient? I mean, within that class, but that is not recurrent. Sir, because in the previous diagram, what you have drawn, from 1 we can move to 3, but that were 2 different classes.
Yes. Yes.
So I am saying, sir, can there be a state within the left class that is transient to some other state within that class, but not recurrent?
No, there is no, the notion of transient is not with respect to something. It's a universal truth. A node is transient or not. That's all. Right? So when do you say a transient? If a node can communicate with something, if a node can reach some other node, I communicates with J, then J should be also be able to communicate with I. Okay? It should not be one-way path. That's what it says. It's always two-way paths that you should have. Okay, then we say that it's a
Recurrent.
right? Otherwise, it's transient. See, the issue with 0, 1, 2 here is that there is a one-way path to 3, not the two-way path, right? That's the problem. See, all that we need to identify is 1, right? 1 has a one-way path to 3. And since 1 can communicate with 2 and 0, all of them have one-way path. That's all. That proves everything, right?
Yes, sir. Yes, sir.
Okay. Can you formally write this proof? Okay. Is that fine? So how do you prove that? So what is the proof technique? So you assume that one of the node is transient. So I have to prove that all the nodes in the communicating class is transient, right? Now you arrive with a contradiction. Suppose not. Okay, so there is one special node, let's say this node, which is not transient. Okay, that means it's recurrent. So what does that mean? You take any node that this node communicates with, they communicate back and forth. Do you agree?
Yes, sir. This essentially brings the question that you just, I mean, you refined my question to that question. Like we can separate a Markov chain in terms of transient and recurrent states.
So no, that's what I'm trying to prove, right? I'm trying to prove that this is not possible.
Yeah.
I'm saying all of them are transient, but in a communicating, see, you have a communicating class, and I'm assuming that there is one, all of the nodes are transient, but one. There's one node which is not transient, it's recurrent. Now I have to arrive with a contradiction, right? How will you arrive with the contradiction if you assume that there is one node which is recurrent? If this is okay, intuitively, let's look at this. If this is recurrent, what do you mean by that? If you let this Markov chain run, the Markov chain will visit this state infinitely often. Do you agree? Do you agree?
Yes, sir.
If you run it forever, it will reach this, it will visit this state infinitely often, right? So whenever it visits, of course, there is some path like this, right? Because it's in a communicating class. It will communicate with one of the nodes in communicating class, right? Do you agree? Back and forth. So if it visited this state infinitely often, a fraction of the times it would have visited the states in the communicating class also, right? All the nodes in the communicating class. Do you agree? Do you agree with this?
All the nodes are registered. The nodes are transients, right? So
that contradicts the assumption that it's all of them are transient, right? It cannot happen. So therefore, you cannot have one recurrent and others transient, or multiple recurrent and multiple transients in a communicating class. Either all of them should be recurrent or all of them should be transient, right? So now what we have proved, we have assumed that all of them are. So we have proved that if node is recurrent in a communicating class, all the nodes should be recurrent. Similarly, you can prove transient, right? Sorry, if all of the nodes and if one node is transient, all the nodes should be transient. Recurrent also you can prove similarly. Okay. Can you write the formal proof? So I want you guys to write the formal proof. It's not difficult. Okay, just building upon whatever I explained, contradiction. Is that fine? Yes or no?
yes, sir.
Yes, sir. Yeah.
Okay, fill this. I mean, it's a fun thing to do. Okay. So now, if you have a state or a Markov chain, so essentially, if you run the Markov chain, you will go back and forth, wander from one state to the other. Some of the states are visited infinitely often, some of them are not, and so on. Right? Now, supposing, let's say, if you take a state I, okay, assume that you can start at I and you can come back to I with some non-zero probability after n step. Okay, so let me write that. So you have a state I, you just wander and come back. Okay, so the probability of you start at I, come back to I after n step is non-zero. Okay, that means there is a n step cycle, right? I start from I, come back to I after n steps. Okay, well, I would say it's a cycle, right? Fine. Okay.
Yes, sir.
Yeah. So basically, it's not just a cycle. So, for example, in between also, I could have come back to the state, go again, and come back, and so on. But in general, I have a step walk that starts at I and ends at I. Okay, so I'll call it as a walk rather than a cycle. Okay. Now, it's possible that for different values of n, this PII of n could be greater than 0, right? I'll collect all those n's. For example, let me give an example. So maybe I'll write a diagram. Okay. So maybe this is, I don't want to do this. It's quite complicated. 2, 3, 4. Okay. This is a Markov chain, okay, with certain probability. Okay, I won't. So what is the probability? If you want to make it more interesting, I'll do this half. Okay. Otherwise, it's a boring Markov chain, right? It will keep on circling. Okay, is that fine? Now, let's look at P11. So I start at 1. After one step, I can come back, right? You agree? Because with a probability of half. I start at 1. Can I come back to 1 in 2 steps?
No, at least 3.
No, I can, right? So one way is, I can start here, come back to 1, and then again come back to 1. Right? That's like 2 steps.
Oh,
right?
yes, sir. Yeah.
So I can do that, right? So this is also great. P1 in 3 steps. Yeah, I can go to
Yes.
yeah, I can go to 2, 2 to 3, and 3 to 1, right? This is greater than, and so on. So essentially, if you collect all those n for which PIIN is greater than 0, I'll get 1, 2, 3, 4, and so on, right? I get a sequence of
Sir,
numbers. Yes.
sir, going from one position to another position in
Hmm.
2 steps,
Hmm.
it doesn't mean that the in between there should be the another stage.
Not necessary. I said that's why I said it's a walk, right?
Okay, okay.
Slightly confusing. A walk is what? Just take any direction, any
Yes, sir.
road, nothing. That's a walk, right? It's not a
Yes,
path.
sir.
Okay,
Okay, sir.
path is where you should not repeat. You should not come back to the same node again and go forward, right? That's not a path.
Yes, sir. Yes, sir.
That's not a walk. Sorry, that's not a path, right?
Okay, sir.
Okay, so now you collect all these, and I will take the GCD of this. You know what GCD is? Huh?
Yes, sir.
Greatest common divisor of all these. Okay, that is called the period of a state I. Okay, is that fine? So what is the GCD of this?
One only.
1, right? If the GCD of a state is 1, that state is called aperiodic. Okay, if the state has some GCD of, let's say, 2 or 3, it's called a periodic state. Okay, okay, is that fine? So let me write that as a formal definition. Okay, the period of a state I, denoted D of I, is the GCD, greatest common divisor of those n, okay, for which Pii of n is greater than 0. If D of I equal to 1, then I is called aperiodic state, or the state I is called, then the state is called aperiodic. Okay, so otherwise it's called periodic. Is that fine, everyone? Okay,
Yes, sir. Yes.
so what do you think is the period of oh, okay, this is a not so very interesting example, right? So let's make this, okay, 1 here. So what is the period of 4, state 4? See, if I start at 4, I can only go to 1. If I start at 1, I can go to either 1 or 2, right? If I go to 2, I can only go to 3, or I can stay back at 2. And 3, I can go to either 1 or 4, right? The minimum would be what? 1, 2, 3, 4. So P 4 of 4 is greater than 0. So 4 is one of the numbers. What about 5? I can always do, right? At 3, I can take a stop and go back to 3 again and then come to 4. 5 is possible, right? 4 is possible, 5 is possible. What about 6? I can always do 6, right? I can stay back at 2 and come to 3 and stay back in 3 and come to 4. So 6 is also possible, 7 is also possible, and so on, right? What is the GCD of all those? 4, 5, 6, 7, etc. What is the GCD of that?
1, sir.
1, right? So it's an aperiodic state. Is the GCD clear? Well, we will see why this is useful soon. Okay, is that fine?
Yes, sir.
Okay. Now, there is a very interesting result. So, okay, so maybe let me not state the theorem. Maybe let me just try to convince you and then probably prove this theorem. Okay, suppose I have, let's say, 2 classes. Okay, you know what class is, right? Of course, there is a link here. It's not separate class, so it's okay. There are no both way communications, but only one way. Okay, you either go there and something like that. Okay. Okay. So now you have these two communicating classes, and suppose I have two nodes here. Okay, I and J. Okay, two nodes. Okay. So now the period of node I is d of I. Okay. What can you say about the period of node J? What is this? Can you say something about the two nodes? That's the question, right? So, what can you say about this? See, pictorially, this is what I can say, right? See, d of I is the greatest common divisor of the number of steps that you need in order for you to start at I and come back to I with non-zero probability, right? So this is the greatest divisor. Now, I can go from I to J. Do you agree? But
Yes, sir. And also J to
I
I.
cannot write it like this, but I can write like this, right? You go to all the intermediate states and come back to J, right? So that means I can go from I to J in some n steps. Do you agree? Because it belongs to the same
Yes, sir.
class, so there is some n for which Pij n is greater than 0. Do you agree?
Yes, sir. Yeah.
Okay. So Pii going from I to I after some steps is also greater than 0. Do you agree? Well, after some step I won't write. After some step is also greater than 0, right? Do you agree? So for example, some multiple of d of I, right? So that will be greater than 0. Now, I can go from I to j in n step. Okay. I can go from j to m, right? So I can wander and go back, so j to I. So pji after m step is also greater than 0. Do you agree? Do you agree?
So it can be a transient class also. I mean,
No, we have already proved that, right? If you have in a communicating class, you will either have a transient or recurrent, right? You agree?
then this class can be a transient also. I mean, this whole thing.
So now what will be the period of a transient class?
So it can never come back.
Right?
Aperiodic.
It's not even aperiodic. It never
It's,
comes back. Okay, let's not worry about
okay.
transient. Let's assume
Okay.
for a moment that this is a
Recurrent.
recurrent. Okay, so let's see what happens if it's transient later. Okay, this is a recurrent, and therefore all the nodes in the class is recurrent, right? So now Pji of m is greater than 0, Pij of n is greater than 0. Therefore, Pii of m plus n is also greater than 0. Do you agree? See, I can go from I to j in n step and from j to I in m step. Therefore, I can start at I and come back to I in m plus n step. This is fine, right?
Yes, sir. Yeah.
Very clear. So that means, this means d of I divides m plus n. Do you agree? You should, right? Why? D of I is the greatest common divisor of such Pii of k, right? Greater than 0. So if it divides is the greatest common divisor, therefore it should divide any step of any walk of length m plus n.
Yeah. Yes, sir. Yes, sir.
Is this clear, everyone? This is
Yes,
important.
sir. Yeah.
Others?
Yes, sir.
Ayush?
Yes, sir.
Okay. I don't know whether Nitish is there. No, I don't see those guys. Okay. Praveen? Okay. So now I'll do one more simple thing. See, I go to J. Okay, so let me write that as a separate diagram. I start at I go to J. Okay, so I wander and go to J. And then from J, I wander and come back to J. Okay, is that fine? Is that fine? Okay. And then from J, I can come back to I. Okay. So what is this number of steps? This is n step. This is m step as before, n plus m. So there is a cycle from I to J and J to I, right? So n plus m cycle. Now let's suppose that J to J, it takes t steps. What is this saying? P J to J in t step is greater than 0, right? Do you agree?
Yes, sir.
Right. Okay. Now, if J to J in t steps, now Pi to I in m plus n plus t steps is also greater than 0, right? Do you agree? I can
Yes,
go
sir.
from I to J with non-zero probability in n step, and from J to J itself with non-zero probability in t steps, and from J to M in non-zero probability in m steps. So the probability that I'm going from I to I in m plus n plus t step is non-zero, right? Very clear. Because I can write this as summation over all possible transitions, and one of the term is this, and therefore I can write this. Okay, is this fine, everyone?
Yes, sir. Yeah.
So this
Yes, sir.
implies d of I divides m plus n plus t also, right?
Yes, sir.
So now, what can you say about this thing now? What can you infer from this? Is this fine? What is what can you infer from this? Can somebody tell me quickly?
So we can infer something about dj also.
What is that?
So from J to J, we can go
In t
in the
steps.
same number of steps here, I think. Yeah.
Also, that's correct, right? D of J, right? That divides what? T. Do you agree? Why is that? Pjj of T is greater than 0. That means D of J, that is the greatest common divisor of J, divides T, right? Do you agree?
Yes, sir. Yeah.
Huh?
Yes, sir.
So this implies D of I also divides T, because why? It divides m plus n also, therefore it should divide. See, it also divides m plus n plus t. That means you should divide t, right? You cannot have add some number.
Yes, sir. Yeah.
Very simple, right? D of I
Yes, sir.
divides t. So D of J also divides t. What can you say about the two? What can you say? What can you say about this?
Multiple of each other, di
Huh?
and dj. Di and dj, multiple of each other.
Can you
Not sure.
argue out why that is the case?
Sir, di divides t, that is t equal to some integer times di. T
Correct.
equal to dj divides t, so t equal to some other integer times dj.
Okay, let's write that. So some L times D of I equal to some K times D of J. Okay, so what? So what can you say from this?
It's like LCM, sir. LCM.
Not really. So essentially, this is the point is this is true for every tree, right? This is true for every T. That is possible, of course, every T possible, right? So that means if you can pick any T such that Pjj of T is greater than 0, that means it's true for definitely for 2T. Do you agree? If I can start at J and come back to J in T steps, I can also start from J and come back to J in 2T steps because I'll go back and forth, right? Right? So that means d of I divides t and d of j divides t. Well, it's true for any possible t, right? That we can have. So that implies d of I, d of I divides d of j, right? Okay. Is that fine or no? Is that fine?
Sir, can you tell me once more, sir?
See, I have taken some t, right, such that pjj
sir.
of t is greater than 0. It's any t that you take.
Yes, sir.
All that I'm saying is d of I divides t and d of j divides t,
Yes, sir.
right? So remember, okay, now let's collect all the t's, okay? So let's say t1 is 1 such t, t2 is 1 such t, and
Sir,
all that.
these are the GCD of all this T, no, sir?
Exactly, d of I divides
Yeah,
all
that's
these,
right.
right?
Yes, obviously,
Therefore,
sir.
d
Yeah.
of I is the GCD of all the t's. That is nothing but, well, GCD of the node j, right? Which is nothing but
Yes,
d
sir.
of j, right?
Yes, sir.
Is this clear? Therefore, d of I and d of j should be equal, right?
Mm.
Is that fine?
Yes, sir.
See, d of I divides t for any t such that pjj of t is greater than 0. So what does that mean? It means that, well, it's not, sorry, I take this back. It is not GCD, right? It is just this. D of I divides this. So that means what? D of I is a divisor of T1 and T2, T3 and so on. Therefore, it is definitely less than or equal to,
DJ, sir.
right? Because
DJ is
D
a
of J is the
GCD.
greatest common divisor of T1, T2 and so on. This is a divisor, right? Therefore, it should be always less than or equal to D of J. How do you complete the proof now? I've shown D of I is less than or equal to D of J. So what is the other thing that I have to do?
So opposite inequality.
Exactly, right? You interchange the roles of I and J.
Yes, sir.
You'll get D of J is interchanging the roles of I and J gives D of J, sorry, less than or equal to D of I.
D5.
So if we call 1 and 2 implies 1 and 2 implies D of I equal to D of J. So this results in the following theorem. I'll write the theorem and I'll ask if you have any, for any Markov chain, okay? So finite or countably infinite states with S countable. I'll write it like this. Okay, S countable. All states in the same class have the same period. All states in the same class have same period. For transient class, I'll assume the period to be infinity. Okay, I'll define it as infinity. So if you have a transient state in one class, all the other nodes are also transient. Therefore, all of them have infinite period. Okay, I think this should work. So is this clear? The proof is clear?
Yes, sir. Sir, in this theorem, sir,
Hmm.
should we define class as a recurrent class? Especially, should we mention or not, sir? Or only class will be enough?
Not really, right? So see, you take any class. If it's a transient, if the node is transient, all the nodes in the class are transient,
Yes, sir.
right?
Obviously.
What is the GCD of each one of them? Infinity, right? So it will never come back, right?
Okay, sir.
Or is it if it is transient, what will happen? So is that correct to say that it is infinity, it will never come back?
Yes, sir. I think, yeah.
See, P, okay, let's look at, not really, right? It doesn't look
Sir,
like.
actually, we can't define there also something like this.
Oh, for example, if you look at 1, right? So starting at 1, I have to come back to 1 in one step, which is 1 by 4. 2 steps. There are 2 paths, right? 1 by 2, 1 by 2, 1 by 4, and then another 1 by 4. So it's 1 by 2. Probability that I come back in 2 steps is 1 by 4. 3 steps, I go to 1, stay 0, stay in 0 for 2 time instance and come back. So it will be 1 by 8, right? 3 steps. 4 steps is 1 by 2 power 4. So n step is 2 power. So it's actually it's the period is yeah, it has some it's a periodic state, right? It's aperiodic because the GCD is one
Yes, sir.
by
One.
definition. So you cannot say that it is the GCD is infinity. The GCD is one. It's called transient because at some point in time it will go out and will never visit. Okay, there is a non-zero probability of that happening. So when that happens, then with the non-zero probability, you may not come back. That means if you look at the long run with probability 1, you will not come back. Okay. Is this fine? Do you have any questions regarding this?
No, sir.
Huh? So others, is the proof clear?
Yes, sir.
Yes. Okay. So Rishabh,
Yes, sir. Yes, sir.
Raveen.
Yes, sir.
Okay. So what is the big picture now? So we have seen that if you have a Markov chain with like if you have a communicating class, and if a node has certain period, then everyone will have the same period. Okay. Now, suppose I have a Markov chain, okay, where all the nodes are recurrent. Okay, all the nodes are recurrent. Is that fine? If all the nodes are recurrent and they have the same period, okay, and the period is 1, what does that mean? It's aperiodic, right? So you have all the nodes like this, and all of them can communicate with each other, and it's one big class, and the period is 1. Therefore, it can, you know what that means. It's aperiodic and recurrent. What will happen? So if you start at node I, okay, so I can reach any node in some k steps. Do you agree with non-zero probability? Right? If you run this Markov chain enough, what will happen? I start at node I, let's say, I'll wander around, and then at some point in time I'll read J, and then I'll wander around a lot of times, right? Infinitely many times. And then I'll enter something, right? Let's say L, state L. After wandering a lot of time, I'll state L. Now, what has happened? You started at I, wandered around and reached J, and then wandered on. Given that you started at J, because of memoryless property, right, of Markov chain, it forgets. So it is as if you are starting your chain, starting from J, and see what happens, right? So it doesn't matter where you start, right? In the long run, this Markov chain looks like it doesn't matter where you start. It matters where you end. If you're asking the question of whether I will end at state L after a long period of time, you should not depend on where you started, right? Intuitively, this is what it says, right? Do you agree? Everyone? Ayush, do you agree with this?
Yes, sir.
Right? So that means if you look at Pij after n steps, so this kind of goes to, in the limit, it should not depend on where I started. It should not depend on J. It should depend on only on J. Let me call that as pi J. And it should also not depend on n, because anyway you are taking n to infinity, right? So after a long time, it will go to pi J. That means if you look at Pij, it goes to pi J, right? It only depends on the column index, not on the row. All the rows will be same, right? The entire row, each term will go to pi J, right? So the whole matrix will go to constant row matrix. Do you agree? That's what it does.
This is essentially the definition of the Markov, right?
No, this is
So
got nothing.
it will not depend on the previous steps.
It's
It will
a
depend on just immediate
previous.
step.
I'm talking about the long run, right? After n step, where n is billion, let's say, right? So it doesn't talk about what happens immediately. It talks about long term, right? If I wait enough, it will kind of forget where it started. It only matters where it ends. And the probability that you end up in J is pi j. Do you agree?
Sir, this is happening within a communicating class, right?
I said this communicating class is one communicating class because all of them are recurrent states. So if all of them are recurrent and the period is 1, then it belongs to one class, right? That is aperiodic and recurrent. It belongs to one class, then it doesn't matter where you start, it matters where you end. Okay?
And so another thing, sir, the definition of Markov doesn't do anything with recurrence
No.
and yeah.
Well, it doesn't say anything about recurrent or anything. Well, it implies, but doesn't say much. Well, it implies, right? Looking at the probability transition matrix, you can say whether a state is recurrent or not. Right?
Yeah.
So,
From
for
constant
example,
group.
if you have something like this, right? 0, 1, 2. So, let's say half, 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 half. Okay. Well, all the states are recurrent. All the states have a periodicity of 1, that means aperiodic. It belongs to one communicating class. So if you let this chain run, right, after a long time, it doesn't matter where it started. It just matters what fraction of the time it spends in each node. That gives me pi j, right? Pi 0 is the fraction of the times you spend in state 0 in the long run, right? That's what matters. Do you agree? How much time, meaning how many times you visit state 0 in the long run. Intuitively, you can see 1/3 of the time you should spend in 0, 1/3 of the time you should spend in 1, and 1/3 of the time you should spend in 2. That's all from this, right? By symmetry. Do you agree? There is no bias towards any state, right?
That means it will tend to uniform distribution.
Exactly, right? It tends to uniform. So pi j tend to be uniform, right? So that means if you have such a Markov chain, you don't need to worry about what happens in the long run, right? If it turns out to be 1/3, then everything works out. Okay. Okay. Anyway, so I'll discuss this in more detail in the next class. Is it okay?
Okay, sir.
Okay. Okay. I'll stop here. And we decided to have a test tomorrow, right?
Yes, sir.
17th evening I'll start, huh? Is that okay,
Okay, sir.
everyone?
Yes, sir.
Do you
Yeah.
have any?
Yes, sir.
Okay, fine.
Yes, sir.
Yeah. So I'll let's have a test tomorrow. This test will be simple, and Savan will communicate the logistics. Okay. So either it will start tomorrow evening, or worst case day after tomorrow morning. We will have 24 hours as usual. Okay. Is that fine?
So tomorrow morning.
No, not tomorrow morning. Day after tomorrow
okay.
morning. Tomorrow evening or day after tomorrow morning. Okay.
Okay.
Okay,
One
sir.
of the two, and you'll have 24 hours.
Okay, sir.
Okay. Yeah. Thank you.
Okay, thank you, sir.
Thanks. Bye.
Thank you, sir.
Thank you, sir.
Yes.